Section 5 talks about the alkylation of the alpha position. So remember again, what this entails is taking a ketone or an aldehyde that has alpha hydrogens. And what we do is we treat this with a strong base, either sodium methoxide, or LDA. And if we treat this with LDA, you make the enolate. And then what we do is we this here for now, what we're going to see is we add a primary or secondary alkyl halide, and just like the SN2 reactions we saw before, we will install the R group onto the alpha position. And so this is very important for synthesis because it creates a new carbon-carbon bond, okay? And of course, at the heart of organic chemistry is building up the carbons and making this molecule bigger and synthesizing very interesting molecules, okay? So keep in mind that this reaction is an SN2 reaction. The enolate here is a carbon-centered enolate, and the carbon acts as the nucleophile. And you're going to attack the primary or secondary alkyl group, okay? The carbon that's being attacked cannot be tertiary, okay? So R is going to be primary, secondary, or of course methyl, okay? And this will create your carbon-carbon bond forming event. And this is the key step here, and the reaction occurs through an SN2 reaction mechanism, okay? Now, for cyclohexanone or cyclopentanone, which I'm drawing here, the molecule is symmetrical. There's no kind of ambiguity. But if you take a molecule like this, for example, and you treat this with, let's say this is a methyl group here, okay? This molecule has two different alpha carbons. We have an alpha carbon on the left, and we have an alpha carbon on the right. So if we treat this with a base, it's possible for us to get the enolate on the right, and that would look, something like this, okay? And remember that we show this as one of two resonance structures. Usually when we're going to attack something or doing a mechanism, we show the enolate on the right. But I just wanted to show you this structure here, because if you look at the alkene, you can see that the alkene has a number of different carbon atoms attached to it, okay? It has 1, 2, 3 carbons attached to this alkene part here. So we say it's kind of like tri-substituted, okay? Now, if we take the other alpha hydrogens on the left and deprotonate them, we can form an enolate that looks like this, okay? And once again, we can draw a resonance structure to show how, the negative charge is on the carbon. And normally we use that enolate resonance structure in our mechanisms to show how it attacks an alkyl group of an alkyl halide. Now, if we count the carbons attached to the alkenes here, we can see that there are 2 carbons attached to the alkene. So we say that it's di-substituted, okay? So the thing to remember from the alkene chapter is that if you have a more substituted alkene, it's going to be more stable. So a more substituted alkene is more stable, okay? So if we were to compare these two enolates, we would say that this enolate here, okay, remember those resonance structures are averaged in the real hybrid, is going to be more stable than these two, okay? So let's take a look at what that means, okay? The book. So This here highlights the situation, okay? We have energy over on this axis, and we have the reaction coordinate on the bottom, okay? And we know how this works. So we have one reactant, and we have a base, okay? And the base can make the more stable, more substituted enolate. And because it's more stable, it's lower in energy, okay? Remember, this is the energy scale over here. So more stable, more substituted, it's lower in energy, okay? This one up here is less stable. It's less substituted, okay? It's higher in energy, and so it's plotted here on the graph, okay? So if something is more stable, we call it the thermodynamic product. If something's less stable, we call it usually the kinetic product. And it turns out that if you look at the activation energies, okay, that's this height here, that is the lowest activation energy if we compare the two curves. So it forms faster, okay? So remember from chapter 6, I believe it is in our textbook, a low activation energy, okay, corresponds to a faster rate, okay? And if something forms faster, we call it the kinetic product. Okay, well, the activation energy isn't called the kinetic product, but the lower activation energy leading to that product is called the kinetic product, okay? So it leads to the kinetic product, okay? Because it forms faster, okay? Now, these are in equilibrium, okay? These are in equilibrium. So if we treat it with sodium methoxide, we'll get the thermodynamic enolate. So let's summarize the reactions, okay? If we take a ketone that has two different alpha hydrogens, okay? And we treat this with sodium, sodium ethoxide, okay, followed by let's write Rx. What we're going to get is the thermodynamic enolate and the thermodynamic product, and the let me use the same colors here so we don't get confused. So what we're going to do is install our green R group, the new alkyl group, onto the more substituted carbon, okay? So this is going by the thermodynamic enolate, okay? So that's just something you need to memorize if you want to learn why and how. Those are the couple slides, but this is the summary here. If you take an unsubstituted or an unsymmetrical ketone or aldehyde, and you treat it with sodium ethoxide, which is in ethanol, which causes it to be in equilibrium. Then when you add the alkyl halide, you get substitution at the more substituted carbon, okay? So you substitute the more substituted alpha hydrogen, okay? Now, in contrast, if you take the same starting material, okay, so let's draw it all out with those green alpha hydrogens, okay, and we treat this with LDA. Now, LDA is in a non-protic solvent. There's no ethanol or anything in there. In fact, we do it in THF, which is an aprotic solvent, and then we treat it with an alkyl halide. What we get is substitution on the less substituted alkyl halide, okay? So there's a great deal of control here. So this goes by way of the kinetic enolate, okay? We want to do reaction or substitution at the less substituted alpha hydrogen, okay? So so that's the summary there, okay? Now the way I remember this is if you have a ketone, okay, like this, and you treat this with LDA and methyl iodide, what do you get? Okay, well, I like to think of LDA. Remember, LDA stands for lithium diisopropyl amide, but here we're going to define it as a different set of abbreviations, okay? So else is going to stand for look for the least deprotonated, least substituted carbon. Okay, so let's do that together. Here's the alpha carbon, here's the alpha carbon. And you want to count the number of carbons attached to that alpha carbon. So this has 2 carbons attached to it, okay? And this carbon has 1 carbon attached to it. So that's the least substituted carbon. D, we're going to use a different abbreviation. We want to say deprotonate, okay, deprotonate. So how do we draw a deprotonation? You take your ketone that we're starting with, you need to draw in that hydrogen, and here's a base, okay? Don't worry about what LDA looks like. This is a base. We're going to deprotonate the least substituted carbon, okay? And that gives us this enolate, okay? Draw the little negative sign there. Circle it on your alpha carbon, okay? The least substituted alpha carbon. Now, what does A stand for? A stands for attack, okay? This is the attack step. You want to attack your alkyl halide. In this case, it's methyl iodide. So let's draw that out, CH3I, and let's draw our nice little curved arrows here. And this is an SN2 reaction, okay? It's an SN2 attack. And that's going to give us the final product, where, of course, the methyl group is now on the right carbon. So we're going to form our starting molecule. It looks kind of like that. And then now you just need to add a line, okay, on the right alpha carbon, okay? So LDA stands for look for the least substituted carbon. D is deprotonate. And then A is attack your alkyl halide. In this case, it's methyl iodide. All right, let's do some practice problems to make sure we understand this. Problem 33. For each of the following reactions, predict the major product and propose a mechanism for its formation. So LDA, we just did this one here. You want to look for the least substituted alpha carbon. You want to deprotonate it, and then you want to attack to form a new bond. So that's going to be your starting material, okay? And then at that dotted carbon, you want to draw a line, okay? That's how we indicate a methyl group. In this case, sodium hydride is operating like sodium methoxide or sodium ethoxide. It gives you the thermodynamic product, okay? So here we want the more substituted alpha carbon. We want to deprotonate that and attack. So you're going to draw your starting material here, okay? And then you're going to add the CH2 and then the phenyl group, okay? So this group right here, the CH2 phenyl, is right here. This is your R group, okay? This is the R group of your alkyl halide, okay? Part C, I don't want to overwrite or write behind my little picture there. So we'll erase some of this content here. If you're taking notes, go ahead and just write it out. I'm going to erase these here. So I have some writing space to write for the video, okay? So what I want to do here is draw my starting molecule, okay? And then we have LDA, okay? LDA looks for the least substituted side. There is no least substituted side. Either of these carbons has one carbon, a total of 2 carbons attached to it, right? So we'll just pick the one on the right. We deprotonate and we install an ethyl group, okay? Ethyl iodide is going to be attacked. Then we treat this with LDA again and then methyl iodide. So now we want to look for the 2 alpha carbons and then identify which one's least substituted. So this carbon is tertiary because it's bonded to 3 total carbons. This carbon here is secondary because it's bonded to 2 total carbons. So it's the carbon on the left that's going to become deprotonated and then attack methyl iodide to give you a methyl group. Okay, so just draw a simple line there. Okay, so that's how you do part C. For the mechanisms, it's going to be just like we showed before, but since this is a video and people can skip through this if they know this already, you can do that. But we wouldn't spend this much time in class, but let's go ahead and just show the mechanism. So here's my starting molecule, okay? And I want to highlight the least substituted carbon and the alpha hydrogen attached to that least substituted alpha carbon. And then I want to draw my LDA. So here's my diisopropyl amide. The lithium is a spectator ion and we don't need to do anything with that, okay? So we're going to deprotonate the alpha carbon here. And this is going to give me the enolate, okay? And then we're going to treat this with methyl iodide. So we want to draw out CH3I, okay? This negative charge is going to attack in an SN2 process to kick off the iodide, which is an extremely good leaving group. And so I'm just going to add a methyl group. Okay, I don't need to write CH3. You could, if you want, you could draw all the hydrogens in as well. Okay. The next molecule, as we discussed, is the 2-methyl cyclopentanone. And if we treat this with sodium hydride, okay, let's draw in that hydrogen. So what we want to do is deprotonate this one here, okay? Because sodium hydride is going to lead to the thermodynamic enolate. So here's hydride. We're going to create the enolate on the left-hand side of this molecule. So that line is a methyl group, okay? And we're going to treat this with benzyl bromide. So I'll squeeze it in like that. And so in yellow here, I'll draw the curved arrow. So the electrons here are going to attack this carbon and kick off the leaving group. And of course, that's an SN2 process, okay? And so what that's going to give me is an additional some additional carbons that are attached, okay? So I want to draw the CH2 group here. And then I want to draw the phenyl, okay? I'm drawing the CH2 just to over-explain things here on the video, but you could just use a line, okay, for that. All right, in part C, let's draw the mechanism for that. As I mentioned, there is no more substituted side, so when we have LDA, we take the diisopropyl amide, okay, draw the arrow pointing to this alpha carbon, and that's how we draw a formation of the enolate. Okay, it's a good nucleophile, it's negatively charged, and that's going to attack ethyl iodide. So ethyl iodide, remember, is an ethyl group attached to a good leaving group, iodide. And so this negative charge is going to attack this primary carbon, kick off the iodo group, and that's going to give me, after this reaction, a molecule that has an ethyl group. So we just draw that with, 2 lines. That's how I indicate the ethyl group. This goes on to react further with LDA and then methyl iodide. So this carbon is less substituted. So in the next reaction, we want to take LDA, or lithium diisopropyl amide. Remember, leave the lithium off. It's just a spectator ion. Point that to the hydrogen and pull the electrons over to the alpha carbon. That's how we show acid-base reactions. And we want to draw the enolate, okay? I never draw what becomes of the amide. I focus on the organic molecule of interest here. And now we want to attack methyl iodide, okay, or iodomethane, however you call this, okay? And that's a nice methyl group that's efficient and sterically free to do SN2 reactions on. So we want to draw out the whole starting material here, and then on this carbon we want to add a methyl group, and we do that by just drawing a line, okay? So that's how you do problem 23. Now, problem 34 is great. It gets into synthesis, and what you'll see here is that we have some common features of this molecule, okay? We have an oxygen attached here, okay? And we have a bond here, okay? And then we have a methyl group, you know, coming down this way, and we have 2 additional carbons coming off that way, okay? Now we have a methyl group over here, okay? And so what you need to do is highlight and very carefully examine what's happening, okay? So basically the whole left highlighted portion of the molecule gets an additional 2 carbons, and there's a new bond right here, okay? A new bond right here. Now what you should recognize is that dotted carbon has a very specific relationship with the oxygen. We can see it better if we draw a ketone here, and now we can see that that's actually the alpha carbon, and that's a key step, and you get that by working backwards. Remember that you can only do alpha alkylations with ketones, right? Ketones, aldehydes. So that's how we're gonna get this this ethyl group here, okay? So that can come from our boring old ketone, okay, without the ethyl group, and then that can come from an alcohol, okay? So we're going to do 2 reactions. We're going to take the alcohol and change it to this ketone. We're going to take the ketone and change it to this ketone, and then we're going to take this ketone and change it to an alcohol. So this is a 3-step synthesis, okay? So in the next slide, write this down if you're taking notes. In the next slide, let me show you how that works. In the forwards direction, we would have this alcohol, okay? And we would oxidize it using PCC or Jones. I'm going to use PCC here today because, I don't know, I just feel like it. Then, this is the key step. We're going to be adding, let's think about this. Do we want to add sodium ethoxide? Or do we want to add sodium, or do we want to add lithium diisopropyl amide? So there's 2 different alpha carbons, okay? And we want reaction at the less substituted carbon, okay? Least substituted carbon. So remember that LDA stands for least substituted carbon, deprotonate, and then attack. So we want to use LDA to selectively operate on the least substituted carbon, which is right here. We want it to attack the ethyl iodide to get a molecule with an additional ethyl group, okay? So 1, 2 carbons, okay? And then finally, we want to reduce this down with, I don't know, sodium borohydride in methanol to give you the alcohol. Okay? So that's how you do these 2 problems. Now let's talk about the malonic ester synthesis. Okay? The synthesis is to take an alkyl halide, and with a few steps, convert this to a carboxylic acid that looks like this. Okay, and if you count the carbons, there's going to be one carbon here and one carbon here. So of course, this is a carbon-carbon bond forming reaction. Okay, and there's some very interesting functional groups. Okay, so you're adding two carbons. The very last carbon is going to be a carboxylic acid, and you're doing that from a alkyl halide. The alkyl halide must be methyl, primary, or secondary. Okay, it cannot be tertiary. Okay. What is a malonic ester? A malonic ester is something that looks like this. We call this diethyl malonate. Okay, and you probably want to memorize this structure. A lot of professors don't like to draw this out. They just might say, starting with diethyl malonate and a suitable alkyl halide, how would you make this? Or they might say, using the malonic ester synthesis, how would you make this? So you need to memorize diethyl malonate in case somebody doesn't write it all down. Okay, so in my class for my students, I'm telling you, memorize this. Okay. Now, how does this work? Well, remember that these alpha hydrogens here are particularly acidic. They can be easily deprotonated because the negative charge that's generated at that alpha carbon is extremely resonance stabilized through the oxygen on the left, through the oxygen on the right. Okay? So the diethyl malonate is acidic. pKa 9, I forget what the numbers are, but it's very acidic, okay? So if you treat this just with hydroxide or ethoxide, remember normally you use the same alkoxide as the ester to prevent trans-esterification, but this guy right here will deprotonate here quite readily to give you the enolate, okay? And this is review, we've talked about this before, so great. Now we've recalled how it's acidic, okay? Now the new thing is that remember that enolates can attack alkyl groups, okay? So if we add methyl iodide or ethyl iodide, it's possible for this to attack it. Okay, so this is recall review number 1. This is to recall review number 2, that enolates are nucleophilic, okay? So this right here is nucleophilic. Okay? And let's use, I don't know, methyl iodide here as a suitable guy. Okay? So this right here can attack a methyl group, okay, to give you, after reaction, diethyl malonate that now has an introduced methyl group there, okay? Now, what we can do is a third thing. So here, let's start with this on the next slide. This is the third thing to recall. So let's draw out our diethyl malonate with the methyl group, okay? And so here we want to recall hydrolysis of esters. In chapter 19, we learned how an ester can react with water with some acid catalyst to give you a carboxylic acid, okay? So, you know, review that whole thing if you forget from chapter 19. So if we treat this with H3O plus, the reaction produces a 1,3-dicarboxylic acid. Okay? Now the new thing, the only new thing here that we're really talking about is that this substance is unstable and it decomposes to form carbon dioxide and a carboxylic acid. So let's draw that, okay? So here's CO2 right there, okay? And if you warm this up, not a whole lot of heat is required, and it's a very rapid reaction. You're going to form the carboxylic acid that looks like this and CO2, okay? So this group right here came from the methyl iodide back on step 2, okay? So that's where the methyl group comes from. The methyl group eventually comes into this position here, okay? The carboxylic acid comes from the starting diethyl malonate, okay? Now let me talk a little bit about the new reaction here. We've talked about alkylation, we've talked about deprotonation, we've talked about acid hydrolysis back in chapter 19. I don't want to review all of those reaction mechanisms, okay? I want to review the new thing, okay? Why is this carboxylic acid, or how the 1,3-dicarboxylic acid decomposes? So first of all, let's discuss how. So if I have my carboxylic acid, okay, and on this carbon I want to draw a carboxylic acid, but I'm going to draw it in this fashion here where the hydrogen's pointing this way, okay, and I'll draw in my methyl group, remember? So here's my 1,3-dicarboxylic acid with the methyl group at the alpha position, okay, and this undergoes a reaction like so. To give you, if you write all the arrows, what you'll see is we have a kind of a decomposition to form CO2. Now, this reaction is not in equilibrium. CO2 is a gas, okay? It's going to escape from the reaction mixture. And remember, from equilibrium, if you remove one of the products, you're going to drive this reaction to completion. So that's why this reaction goes all the way to the right, or how it works is the arrows, and why it works all the way to the right is because CO2 is a gas and it just comes out of the reaction, okay? Now this is an enol, okay, a weird looking enol, and we know that that's in equilibrium and much more stable as the keto form, or the ketone, so to speak, of the enol, okay? So that's going to tautomerize to give you the more stable carboxylic acid tautomer, okay? And that's done in H plus catalyst, which is present from the previous step, which was H3O plus, okay? So that's present in all of these steps. So that's how it works. Let's look at the overview, okay? So starting from diethyl malonate, we want to treat this with sodium ethoxide. We want to treat this with an alkyl halide. Okay. We want to treat this with a little bit of acid and heat. Okay. And let's mentally or conceptualize what's going on here. Okay. So here's the alpha hydrogen. We know that we are going to deprotonate there and attack the alkyl group of my Rx, right? So the R group is going to be attached here. Okay. And then H3O plus creates the carboxylic acids, and one of these gets expelled, okay? So this whole group goes away. And what you get from this chemical reaction is your R group attached to the right-hand portion with your carboxylic acid. Okay? These are the 3 steps you need: base, alkyl halide, acid, and heat. Now, you can do this twice, okay? Look at this chemical reaction. We can take diethyl malonate and I just want to refresh our memories that this carbon has 2 alpha hydrogens. So it's possible to treat this with sodium ethoxide, okay, followed by an alkyl halide. Then rinse and repeat. Treat this with sodium ethoxide and then a different alkyl halide. And then at the end, do your H3O plus and heat, okay? And so what we're going to form from this chemical reaction is a carboxylic acid where we have 2 different R groups attached to the alpha carbon of our carboxylic acid, okay? We're going to have the first R group attached, and we're going to have the second R group attached, okay? So that can form more than one kind of bond, okay? It can form 2 bonds. Now, sometimes you can form cyclic acids, okay? And it looks like this. So, for example, if you add sodium ethoxide to this, okay, and then something like this, let's work through this stepwise. What you're going to form is something that looks like this. Okay, there's 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons, okay? And then you can treat this with sodium ethoxide, again. So that makes the enolate here, and that's going to attack here and kick off the bromide, right? So that ring is going to be 1, 2, 3, 4, 5, 6 carbons. So that's going to make something that looks like this. Okay, and then we can do the usual thing, H3O plus and heat, and that, remember again, converts this to the carboxylic acid and removes one of these, either the left or the right, it doesn't matter which. So the final molecule here is going to be cyclohexane carboxylic acid, okay? So that's pretty dang nifty, okay? Let's do some practice problems now. Now, keep in mind at the university level, even the community college level, most professors will say, okay, that's how it works, let's go on to the next subject. But since I'm on YouTube here and people have the opportunity to skip ahead to the next part of the lecture, I'm going to pause to do some problems right now, right here, while this concept is fresh in your mind. If you're only interested in the concepts, then skip the practice and practice on your own with how you see fit, okay? So in part A, what you want to do is think backwards through all of these, okay? And so what we have is this carboxylic acid right here, and you want to circle that first alpha carbon, okay? And your R group is going to be here, if I may circle it, it's right here, okay? Attached to the beta carbon, okay? So you want to keep the beta carbon with your R group, okay? And you want to keep the alpha carbon here with your diethyl malonate. So don't miscount the carbons or accidentally include the carbon with the wrong starting material. So it says propose a synthesis. So in part A, what we would do is we would take diethyl malonate, okay? And that's the alpha carbon that I've highlighted there in blue. And so 3 steps here, right? We would add sodium ethoxide. We would add this very interesting alkyl group, okay? And this is going to become the beta carbon. It's not the beta carbon of an alkyl halide, but it's the blue beta that I've highlighted in the final product that we're trying to synthesize. And then remember, you would add H3O plus, and don't forget to add heat, okay? And that's going to give you the molecule that we have right there. Let's do molecule B. In molecule B, let's use the same kind of designation. So here we are. Okay, here's our carboxylic acid. This carbon right here is the alpha carbon, and that's going to be the carbon of our diethyl malonate. This carbon right here is the beta carbon of one alkyl halide, and this carbon right here is the beta carbon that will come from a different alkyl halide. So this is like those examples I showed you before. You're going to do this twice. So you're going to do diethyl malonate as your starting material as usual. Okay, and so that's our alpha carbon. In the first step, you're going to treat this with sodium ethoxide and perhaps methyl iodide. Okay, so that'll stick on a methyl group. Then you want to rinse and repeat, so sodium ethoxide. Okay, and what alkyl group do we need here? We need the 6-membered ring, and we need that beta carbon there. So you need to make sure that you have that carbon, and then put a good leaving group there. It could be bromine, it could be iodide. Okay, iodine or bromine is good. And then step 5 is always do the H3O plus and heat. Okay. So that's how you get the product there. Okay. How about C? Okay. This molecule is written in a weird way, but here's our carboxylic acid, and here's the first alpha carbon. Okay. So remember that alpha carbon comes from the diethyl malonate, and then we want to think about these other alkyl groups here. Okay, including the beta carbon. Okay. So this is the beta carbon of a carboxylic acid, and here's the beta carbon of a carboxylic acid. So 3 carbons is going to be propyl bromide. Okay, propyl bromide. So let's draw the reactions necessary there. So once again, we start with diethyl malonate. Okay, and we need to install a propyl group, so we're going to do sodium ethoxide and then propyl bromide. Okay, that's 3 carbons. Okay, if you count them out, 3 carbons. And then we're going to rinse and repeat because this molecule needs 2 propyl groups. And then we're going to do H3O plus and heat. So all of those reactions are going to give us this molecule here. Okay. I'm running out of space. Let me create a new slide and do the rest. Following the procedure here, we want to highlight the carboxylic acid and that alpha carbon. Okay, so the alpha carbon comes from the diethyl malonate. And then we want to circle these 2 R groups, right, to figure out what we need to add. So this carbon is the beta carbon, this carbon is the beta carbon. So methyl iodide and propyl iodide, for example. So let's do the synthesis here. We would start with diethyl malonate as usual, and sodium ethoxide would be the strong enough base to do this. Okay, sodium ethoxide, and then we would add, which alkyl halide would you add? Would you add the propyl bromide or the methyl iodide? It doesn't matter, it's up to you. Either would work. So let's add the propyl bromide or propyl iodide first. Then we'll do sodium ethoxide. Then we'll add methyl iodide. And then we'll add H3O plus and heat. Okay? And that'll give us the target molecule. How about in letter E? It looks more complicated, but it shouldn't be any more complicated, okay? So here's our carboxylic acid, and I can't emphasize this enough. Make sure you circle this alpha carbon of the carboxylic acid. The remaining things are going to be your alkyl groups, okay? So this alkyl group is going to be your isobutyl whatever, this is going to be an ethyl group, right, attached to this beta carbon. So let's start with diethyl malonate. We need to treat this with sodium ethoxide. To get the ethyl group on, we'll do ethyl bromide. Bromine and iodine are very good leaving groups. Either would be fine. Sodium ethoxide. Okay. And we would want to add this alkyl halide, okay, with that branching there. Then we would add H3O plus, heat, we get the product. Okay, so for these practice problems that are in Klein, I do hope it helps you analyze how would you make, okay? As usual, practice 3, 4, 5 problems to get a good feel for it, and then practice it once every couple days or something to keep fresh, okay? All right. Acetoacetic ester synthesis. This procedure is going to transform an alkyl halide into a ketone, okay? A methyl ketone, if you want to call it that, okay? So before we did the procedure where it was an OH here, okay? This is a methyl group, okay? This is a methyl group. Not an OH, okay? So it's not a carboxylic acid. So what do? We start with ethyl acetoacetate. Instead of diethyl malonate. Diethyl malonate has an oxygen in place of that methyl group, and that ends up making the carboxylic acid, okay? So this is diethyl malonate. So you use ethyl acetoacetate to make ketones, and you use diethyl malonate to make carboxylic acids. Okay? So guess what? The procedure is exactly the same, except it's a slightly different starting material, and the pKa's might be a little different. Okay? So let me recall or refresh your memory. You always want to deprotonate the middle, okay, the middle alpha hydrogen, because it's flanked by 2 carbonyl carbons. So if we treat this with sodium ethoxide, okay, the most acidic hydrogen is going to be deprotonated, and you're going to form the enolate that is extremely resonance stabilized by 2 carbonyls. Okay? Recall again that alkyl halides can be attacked by nucleophilic enolates. Okay, so if we add a primary, secondary, or methyl alkyl halide to this, we can alkylate the central alpha carbon of this guy here to give you a new molecule where we've introduced a new carbon-carbon bond. Okay? As usual, recall that a ester right here on the left can be hydrolyzed with water, you know, an acid. We just write H3O plus. So that's going to make the carboxylic acid, okay? And then recall that carboxylic acids at the 3 position relative to an ester or a ketone or whatever are going to decompose. So if we add heat to this, this forms with loss of CO2, it gives you the final ketone. Okay, the final ketone. So let me show you how that works. Okay. Ethyl acetoacetate is our starting molecule. We treat this with sodium ethoxide in ethanol. Okay. And we're going to treat this with a, I don't know, benzyl bromide. Okay. Step 3, we do H3O plus and heat. So I've color-coded things. Let's keep things straight. So in yellow, this is my alkyl group, including this carbon. Okay, so this is the alkyl group, the R group. Okay, and that's going to be attached to this ketone. Okay, so here's my alpha carbon, here's my alpha carbon. So these carbons right here end up in the final molecule. Okay, this carbon right here that I'm highlighting becomes the beta carbon of my ketone. Okay, so yeah, that's how it works. Like with the diethyl malonate synthesis, you can do this twice. Okay, so here's example 1. Example 2 would be something like this. Okay, and we can treat this with sodium ethoxide. Okay, and we can treat it with a green colored alkyl group. Maybe that's a methyl. Okay. And let me get my pens. 3, so sodium ethoxide. Okay. And then I can treat this with, you know, not a methyl, but say an ethyl group. Okay, a different alkyl halide. And then I can treat this with H3O plus and heat. Okay. And this is going to form a ketone, right? So attached to that alpha carbon are the 2 alkyl groups. One of the alkyl groups is going to be, you know, maybe a methyl group. One of the other alkyl group might be a methyl group, okay? Now remember that your R groups, whether they're used in the first or the second step, should be methyl, primary, or secondary. No tertiary alkyl groups can participate in SN2, okay, SN2. So that goes back to the first semester organic chemistry. So you can make ketones, okay? So let's go ahead and just jump into some problems here, okay? Problem 39 looks good. Problem 39, we want to use the acetic ester synthesis. Do you see how these word problems are worded here? They don't tell you what ethyl acetoacetate is. Now, when you highlight things, we're going to do the same kind of feature here. We want to highlight the alpha carbon on the left of this ketone, okay? And that alpha carbon comes from the ethyl acetoacetate. The beta carbon with respect to the ketone is part of my alkyl group, okay? So this right here comes from my alkyl group, okay? So the synthesis is going to start with ethyl acetoacetate, all right? So that's a methyl group on the right, the methyl group. And so what we want to do is treat this with sodium ethoxide and, you know, ethanol, a nice protic solvent there. Number 2, we want to add the alkyl halide. So we want to take that nice 6-membered ring and with the beta carbon that I've highlighted in the structure above and put on a good leaving group, iodine. Okay, iodine's a great leaving group. Step 3, H3O plus and heat. Okay, and that'll give me the target molecule. I'm done. In B, be careful to highlight the alpha carbon in your starting structure, okay? Like so. And let's highlight it and label it, okay? So remember again, that alpha carbon comes from the ethyl acetoacetate. And so what are we adding? We're adding a benzyl group, and we're adding an ethyl group, okay? So we want to start with ethyl acetoacetate once again. Treat this with sodium ethoxide, okay? We want to add benzyl bromide, for example. And then we need to get that ethyl group on there, so we're going to do the same kind of procedure with bromoethane. Don't forget, at the very end, you want to add H3O plus and heat. Okay? Molecule C, it's written kind of pointing up on the board, but let's just go ahead and do this one here. Okay? So try not to miscount the carbons. That alpha carbon comes from the ethyl acetoacetate. And then you just want to circle the remaining groups. This is going to be one R group, and this is going to be another R group. Okay? So let's go ahead and do that. What we want to do is start with ethyl acetoacetate. Sodium ethoxide. One of those R groups is 1, 2, 3, 4 carbons. So 1, 2, 3, that's 4 carbons. And then add, a good leaving group like iodide. Sodium ethoxide. And we'll get the second R group on there. That second R group is going to be with the leaving group attached here, okay, to get the isobutyl group. H3O plus and heat, don't forget that at the very end. Okay, that'll give me molecule C. Molecule D, here's my ketone, okay. I've highlighted the alpha carbon there, and make sure you circle that alpha carbon in the purple, part of the ketone there. And so we're going to add a methyl group and a butyl group. So we're going to start with ethyl acetoacetate. Step 1, sodium ethoxide. Step 2, methyl iodide. Step 3, sodium ethoxide. How do you get a butyl group? Bromobutane. Okay. And it's easier for me to draw a stick figure, bromobutane, than to write C4H9I or whatever the formula is, okay? H3O plus and heat, okay? So that's how you do part D, okay? That's it for section 5. We've covered a number of key issues. We've talked about the differences between LDA and sodium ethoxide, okay? Sodium ethoxide gives you the more substituted enolate. LDA gives you the least substituted enolate. We've talked about using diethyl malonate in the malonic acid synthesis. Okay, I'll just draw the structure here to do a whole bunch of reactions to give you a carboxylic acid with some new functional groups. We've talked about the acetoacetic ester synthesis, which is to take ethyl acetoacetate, these weird sounding molecules and names, and this will give you ketones. Okay? Thanks for watching, and please consider subscribing.